Hello, this is Adam Harris, and today I'm going to be going over my involvement in TimothE2D, the game developed by rather ridiculously named Group 7. So my role in TimothE2D was the lead programmer. So I managed everyone's work. I managed the programmer's work. I distributed the tasks. I did Scrum meetings, etc. However, other than the general sort of management aspects, I also did the batch renderer system which reduces our draw calls significantly. I did the tile map, I did the tile map editor, the physics system, scene management, health components, movement components, the character game object hierarchy, all the collision aspects of the game. I did all the fighting mechanics, most of the AI controller and A-star algorithm, I did some of the more component parts of it, so I designed the player input component and player movement component, all of those sort of things. So let's just first off go through my renderer. So the renderer is fairly simple. It has a it's all a static class, so you can access it anywhere. Key aspects of it are the init function, which handles creating our vertex buffers, all our renderer data basically. And there's two different passes. There's the renderer data for the tile map and sprites, and there's a renderer pass for the UI, as they use different shaders, as they have different data that needs to be passed through to them. So for example, the tile map data and all sprites have a light level, but the UI does not. So in terms of how people actually use this, so there was a draw quad function. And well, there's draw quad and draw UI quad. Draw UI quad means I will just use the UI data section as opposed to the renderer data. And then these draw quads, they put together the information. So it takes the quad, texture, UV coordinates, light level, tint color, and tiling factor. Takes these information, creates a transform from this size and position. Then it sends it to the draw quad, which takes a transform. And this here prepares the actual data for the shader. So it says, okay, we've got four vertices in each quad. Here's the texture coordinates. If we aren't passing in UV coordinates, then if we are passing in UV coordinates, then it sets these texture coordinates equal to the ones passed in. If we have exceeded the maximum amount of indices in any given batch, we'll head to the next batch, which flushes the screen and draws what's currently on before restarting this batch. There's a texture index. This refers to the index on the texture. So we're using a texture atlas system. So the shader can have 32 textures stored at any given time. And as you add in additional textures here, it will then push those around. And if it exceeds that, then goes on to the next batch. If not, then it just is like, okay, this quad is using this texture slot, let's assign its texture slot. It reduces the amount of texture binding calls that need to be done, since it's not an expensive operation, but it is slow when it's happening every frame. Since if every object has a different texture, then that is every object binding a different texture ID, which can take a small amount of time due to the data transfer from the CPU to the GPU. So like I was saying, if we exceed our max texture slot, then we go on to the next batch. If not, we just set our texture index, we set all of that stuff. Then here we actually prepare the quad vertex buffer data. So this is the position, so it calculates our transform position, our tint color, texture coordinates, light level, texture index. All of this goes to the shaders. Now you may be looking at this code and wonder, okay, why is it in four chunks? This is practically the same. The only difference is here. So why is this not in a for loop? Well, I found that unrolling this for loop actually gave us a slight performance increase of about 3 to 4%. Albeit that is within a margin of error, it is still noticeable, especially when we were having issues with optimization early on. So let's go over the physics system. So this is something I was actually very happy with. So the physics system, it has a vector of collider bases. So collider bases are just, well, I'll show you. They are a component they say, oh, this is a trigger. It has a type, so the type is a box collider or a circle collider. It has a scale, which refers to how big the collider is relative to the model. So if the scale is 1, then the collider will be the same size as the model. If it's 5, then the collider is 5 times larger than the model, larger than the sprite. So that vector of collider bases can be stored there. There's also the colliders to remove, so this ensures that if a object gets destroyed during a frame, it gets added to that, and then at the end of the frame, they will get removed, rather than risk messing with data while it's being used in an update method somewhere. There's also the colliding bodies vector. Well, colliding bodies vector of pair collider base to collider base. This stores all the current colliders that are colliding, basically. And this is used so we can do a on-trigger enter and on-trigger exit call, which is, well, it's very much inspired by Unity. So if we look at some of these methods, so you have the add collider, so it just places it back. There is the timlog system, which is a logging system used in the game, and this just outputs the file name and line number. So here it will say, it'll give the file path to this file of a physics.cpp, line 10, number of colliders in scene, etc. So that just helps with finding our logs and doing things in a nice, organized manner. Anyway, add collider adds a collider, remove collider. It adds it to the colliders to remove if it cannot find them. Then there are various intersect methods, and I mean various intersect methods. So we have seven different intersect methods. So you have one that takes in 2 collider quads. So this is something that doesn't. A collider quad is just something that doesn't have it doesn't need the details of if it's a trigger or what. It's just like, oh, this has a position and a size. Let's just see if these 2 things collide. So this can be used for like buttons and stuff. Then you have intersect for bots on bot, a bots on point, circle on circle, circle on bots, circle on point, point on bots. So that's really just so you could pass these in either way around, which technically isn't really needed because of a system I'll show you in a minute. So there's the handle collisions and handle no collisions method. So handle collisions takes in the 2 collider bases, and it's like, oh, okay, let's see if this one's a trigger. If so, then we'll call on trigger enter, etc. It just handles the event on trigger enter and on trigger exits for the objects. This is something that I was really happy with, actually, is the update world method. So it gets our collider type, and so it stores the type of the collider, so a circle or bots. And here, using these if statements, it goes through and says, okay, if A type is a circle and B type is a circle, then we're calling this method. If it's a bots and a bot, we're calling this. If it's a bots and a circle, we're calling this. If it's a circle and bots, it's doing this. So using that system really allows us to just sort of rapidly. It means that I can just call physics update world and it will all update. Now, a limitation of this physics system is that it isn't efficient. If you look here, we're cycling through every collider. So say if there's 100 colliders in the scene, okay, collider 0 to 199. Then we do colliders 0 to 99 again. So that isn't efficient, because that's testing 100 objects against every other 100 objects. If those objects are nowhere near each other, there's no point in testing their intersection. However, due to time constraints and lack of knowledge, and more just lack of wanting to complicate things needlessly beforehand, I didn't do something like a quad tree implementation or like any form of like spatial partitioning. I did quite want to look into a binding volume hierarchy, but didn't get around to the time, especially with all the other tasks that need to be done in the past few weeks. Now, end frame method, this is where it handles removing collider bodies and such. So just search, just searches through the colliders to remove, and it will remove the colliders from the vector of colliders, etc. It's a fairly simplistic method. Right, onto the scene manager class. So this is a static class that just say that we can use anywhere to get the current scene. We can use it to set a current scene, so loading from one scene to another. We can use it to delete scenes, set the default scene. These were primarily used when we had a editor, which we used to do back in, well, we used to have an editor back in the first dev period, but coming out to start the second one, we all sort of realized we did not have the knowledge or the time to make a game and a usable engine in the next few weeks, so we just dropped half of the engine features and just converted it into a framework. There are still some remnants of the engine code around, especially in the editor class. Right, onto health. So health is another type of component, so there is different things. So there's the max health and the current health if it's dead. There's on death, on heal, and on damage, which take in a game object called the instigator, which is basically just saying, oh, this object was damaged by this object was killed by this object, etc. And these on death, on heal, and on damage, they're all protected, so they can be overridden by the base classes of health. So we have player health, structure health, and enemy health. All of these need to do slightly different things when they die. So it was good to have those have the ability to just call on to override these and not have to worry about like calculating the damage they took, since it's just called here and take damage. If it's less than 0, it calls on death. If they've taken damage but not died, then it's on damage. So like there's not too much setup there. You do just override the on damage, on death, and on heal and do whatever you want in there. Another thing I developed was the movement component. So there are multiple types of movement component in the game. So you have there's two movement components. There's the movement component and the AI movement component. So the movement component basically takes in the primary method is the move method. This takes in a movement vector to say, if you want to move to the right, it takes in a move vector of 1, 0. If you want to go up and left, it's -1, 1, etc. This, first of all, this does a magnitude check just to check that. It just gets the magnitude so we're not like moving faster diagonally. So the bug that we originally had was if you'd move left or right, you go normal speed. But if you went diagonal, since you're holding both keys, the vector is longer, so it would actually speed you up. So this just stops that. Then there's this movement check. So this just sees if the move vec is 0 and 0, then we're not moving. If that's not the case, then we are moving. And if we're not moving, then we just return from this method because there's no point in doing it. Then we decide the direction, which is based on basically the move vexing if we're moving left, right, up, or down. Once we've decided the position, we can then go, okay, let's now see if we allow positions. If we allow collisions, then we do a collision check. So this checks the collisions against the tile map. Something that is not good here is this. This is something that has just been put in for the sakes of getting this done in a quick fashion. So these are just hard-coded values saying this is the top hand of the map and this is the right-hand side of the map. These left and bottom values are completely fine since they are 0. But these are magic numbers. They should be avoided. I should know better, but it had to be done. So here, actually, this is an example where I use that collider quad physics instead. So this is where I actually calculate if the penetration depth between the player and a tile, and then correct the position based on that. So an optimization I did here is to avoid the player checking their collision against, we've got about 16,000 tiles on our tile map. It just checks against the tiles in its immediate vicinity. So it's like, oh, okay, I can only collide with the tile to the left of me, above me, to the right of me, and below me. So there's only a point in checking those tiles. Now the character is another aspect of the character game object hierarchy, as I call it, is another aspect that I primarily focused on. So you have the game object, which takes in the name and the tag, and then the character, which takes in the texture, Now, characters are a game object with a movement component, an animated sprite sheet, a sprite component, and an audio source attached to them. Toby did all the audio programming, so I'm not too sure how he's implemented that with this, but we just look here. So first off, we add the texture component, then we set up our animation sheet, add the audio, the movement, set our movement speed, add the sprite, set a default sprite, set the frame rate, and set the scale of the character. So all characters in the game have a default size of 0.25 by 0.45. So this gives you a width of 1 tile with a height of nearly 2 tiles. So it sort of looks like people are around 6 foot-ish. Then there's the unique logic method. So this can be overridden from the game object-based class, and this just lets you do any unique logic to this game object. So the character, for instance, has to update the animation sheet, has to calculate what animation it should play based on the direction it's going. But say like the bed object, it doesn't need this. I don't even think the bed object... Well, no, the bed object does override that because it needs to check if the player's nearby so they can sleep. But in this case, the unique logic method in the character just simply does all the animation stuff for the sprite sheet. Oh yeah, something I did forget to open up actually is the tile map, which is probably where I spent a majority of my work in after the first, well, starting from the end of the first dev period and on to the next 3-4 weeks was spent making the tile map and the tile map editor, as I could just not get the maths correct at all. Yeah, I could not get my maths correct for the mouse position to what tile they were pressing, and it still isn't 100% correct, which is a bit of a shame. But the tile map system, it can be used in a wide variety of games. It's expandable, it's easy to use, you can set a default size, you can use multiple sprite sheets on it, you can fill layers, you can clear layers, you can clear the entire map if you want to. It supports saving and loading maps as JSON files. It's a very reusable system, which I could, in theory, take from this framework and with some minor modifications make it work in anything. However, the render map, of course, would have to be different per framework as it's using the batch renderer. But it would be, in theory, possible to transfer this tile map system to another engine without too much hassle. So, I guess it sort of brings me on to the tile map editor, actually, because this has a lot of stuff to it. So like I was saying earlier, originally we were going for a game engine that sort of looked similar to Unity, and that just wasn't feasible. It wasn't feasible at all in the time that we had to produce a Unity-like game engine and as well a game in it, so we ditched that and made it the framework. But to make it sort of better for the developers, we were like, okay, we're thinking, okay, if we use a tile map editor like Tiled or something like that, that isn't going to allow us to set each individual tile as collidable or not. We'd have to use some form of like second map over it to then say what's collidable or not. That's not amazing. So instead what we were doing is this tile map editor, you can place everything and you can say what tiles are collidable by placing down a collidable tile. So actually, I'll show that off because I'm quite happy with it. So it's booting up the game. Here's the main menu. This was done by Isaac. So yeah, so this is tile map in action. Oh, I also did, this is the character object in action. So you can see the sprite animations. The sword was also my work, and that's part of the... Well, it's a rather bad animation, I will admit that. And there is the resource nodes, which you can mine, but that wasn't what I was showing off. I wanted to show off the tile map. So the tile map editor looks like this. So you have your tile map window here. Oh, it is now switched to night. Whatever, the player can be killed. So say you want to place down a tile here, and there you go. As you can see, it's slightly off. As you can see, it's not perfect. these red tiles are collidable tiles. These green tiles are non-collidable, which is all nice and self-explanatory to the developers, which is something that did take a while to make this tool developer-friendly, since it wasn't developer-friendly at the start. One of the main things was that it didn't say what tile map they were editing, so there was some confusion between the developers as they were like, oh, you work on town scene, the farm scene, there was crisscrossing, there was some overwriting of each other's work. It was not good. The showing collision map also helps with that because it just applies a tint to each tile as it's drawn, saying if it's collidable or not. So to answer some of the questions set out for this, so how reliable is the engine/game? The engine is mostly reliable. There are some issues with the engine. I'm not going to lie and say that it's flawless because it is not. There is still lots of areas where the engine could be improved. For example, I could show off the render loop is a prime example where tech debt sort of got the best of us and we did some things that were not considered amazing. So here we go. So here is our render loop. So we render the tile map first, completely fine. Okay, so we loop through our drawable objects. Yeah, completely fine. Get the object. If it's not active, continue. If it's to be destroyed, continue. If the tag equals player, continue. That's odd. That is not good. And the reason why that is because the renderer system doesn't have a draw order system, really. It just draws in the order that objects are added to the drawable objects list. It'd be much better if, say, for example, you say, okay, this has a draw order of 100, it's above anything with a draw order of 50. That would have helped a lot with this framework, and especially with a lot of the issues, it would make the tile map look a lot nicer as well, because we could reliably say, okay, the players to render in front of this, the players to render behind this. So actually render the scene from beginning to end of the drawable game objects, which doesn't work all the time. It's not amazing, but it does sort of work a bit. Then we have this, which, well, if the tag is UI, then it has to go through the UI draw method. If not, then we check if we have a sprite component. And if so, then we have to get the sprite, get its texture, and get the texture coordinates. If not, then we have to just use the object texture, which could be improved, really. TimothE2D and sprite could really just be sort of combined into one thing. Oh, yeah, and then there's this. So this is a second drawable game object loop, and this checks if... And that basically is saying, okay, let's render the text component, because the text component does not render using the batch renderer. The text component was built by Lucy on her own. I did not have any time to explain how to implement like a batch rendering system to it, so it got rather shoehorned in here at the last minute when we figured out it wasn't working correctly. So yeah, that's one example where the engine isn't typically reliable. And the removing game objects sometimes works, it sometimes does not work. Sometimes there are issues where it will crash. There are issues in the tile map where sometimes it won't render, so you have to restart the game. I don't know, there's a lot of areas where the engine could easily be improved if given the time, and if we all took the lessons that we've learned from these past few months working on this and did it in something new. This could be a brilliant framework if we had the knowledge and time, I believe. So mechanisms to make this more reliable. So there's lots of null pointer checks everywhere. Wherever we're sort of dealing with pointers, we're checking to see if it's a null pointer, just to make sure that we're not ever going to crash from that, because null pointer crashes they're usually not non-recoverable. It will just crash the program, but doing that null pointer check, then it just won't render this object. There is no crash there. Testing conducted was mainly just us sort of going through, playing the game, testing our feature, testing other people's features. It would have been nice if we learned unit testing so we could automate some of these systems. None of us have any experience with that, though, as none of us were being on placement, so we had no idea how to start with that. So how complex is the engine / the game? The engine itself, I would say, is a good base for a 2D framework / game. There's a lot of things in it that still need improving, such as the sprite drawing order, like I've already said. And there is some areas where it could be further optimized. The render loop could be optimized a lot further. And it's also single-threaded, which, well, is a bit 2001. But if we had some more knowledge on how to properly do this, then we could create a pretty complex engine that's fast, optimized, can create pretty advanced games. The game itself we developed probably came together in the last 2 weeks, and it's reasonably complicated for the tools we had. So there's AI controls, there's A*, there's day and night cycle, there's sound effects, music, elements of physics, tile maps, loading scenes. There's farming mechanics, so we can till the ground, plant a crop there, and harvest it on the next day. There's the defense mechanics for actually building objects and stuff, which actually that was something I also developed. So first, show that off. So if we go into B mode to build, something I do need to do is I'll just grab some resources and grab some wood. So if I now place down a tower, by designing. Oh, I grabbed coal, not stone. Yeah, I needed stone. Yeah, this inventory was made by Lucy. Well, the inventory screen was made by Lucy, and the inventory system was made by Toby. Both great systems. Brilliant work from those two. This is a tower that I just placed down, and then here's a wall. So this actually sets the tile to be collidable, so I can no longer walk through it. It also updates the A* algorithm, so the enemies won't try and path through it. You see that my sword is it's sort of behind the defenses, which could be good, but I don't know, there's some areas where I feel the sprite drawing order would be very nice if it was designed from the start. There's also this weird bug here where I believe this is a floating point precision error that causes like this little bug. So like if we snap to an exact coordinate, you can sometimes get lines in. I'm just going to close that up before night hits because that's music gets a bit loud. So the capabilities beyond this single game we created. So this engine, it can do 2D games, it can do overhead games, it can do tower-based games. And the game we have developed is, in theory, a relatively basic version of Stardew Valley with some tower defense elements in it. So we could develop quite convoluted, quite complex games in it if we continue to optimize the render loops, multi-thread the engine, make some of the things a bit more stable and less finicky, and it would actually work quite well. It would be able to create good 2D overhead RPG style games. So inspirations from other engines. At the beginning it was Unity. In fact, the early design documents for the engine, the UI was practically Unity. Hazel Engine by Cherno Project, or Jan Cherikov. He created a OpenGL engine, 2D and 3D, and that was quite an inspiration as well. His C++ series is probably what got a few of us into the language in the first place, and his OpenGL series helped us a lot during learning and process. So yeah, there was some inspiration taken from the Hazel engine. So how does this compare to other frameworks / tools? So if you wanted to compare it to Unity, well, Unity would obviously win because Unity is a full-blown engine. If you wanted to compare it to RPG Maker would probably win again because it is a full framework that people are willing to pay for. I don't think anyone is willing to pay for this currently. However, if you compare it to another free open source engine such as TimothE2D, which is a similar 2D tile-based engine, then this would somewhat outperform it because this has a tile map editor, that one does not. However, Love2D has more advanced physics. This does not. This just has triggers and tile map collisions. So there's definitely ways where this is better than other free alternatives to 2D and ways that it's worse than other free alternatives to 2D. So let's talk about the fun in this. So I'm actually going to load up the actual EXE of the game here. So what I really like in this game, it does just get very intense very quickly. So let's start getting some resources ready, because when the first night hits, it's going to be pretty intense. So I've got some stone, and I'm going to get, well, I've got some wood. I'm going to get some stone because I want to build a tower to help defend my base. Right, so we've got some stone. Let's just try to defend our tower a little bit there. Actually, I'll show off some of the farm mechanics. So we're tilling some ground here. Oh, I untilled that one. I think it would be nice if you could till like nearby by just pressing. Let's toggle farm mode and let's plant me some wheat. Let's plant me some potatoes, some carrots, and now these will grow on the next morning. Right. So night should be coming up soon. Right. So let's just grab some more resources. Let's actually grab a campfire while we're here. So that's made of wood and coal. So let's place a campfire there. And this has done some really nice shader. This is some really nice use of the light level system. This was done by Jacob. It's a really nice system. It looks great. It propagates nicely between multiple light sources. Right. I'm actually just going to sleep because waiting tonight could take a while. One sec, I believe I need a little bit of stone. Oh, okay, I here to place it on top of that. So the game is not perfect. There is obviously bugs in it. Now let's sleep till night. Oh. To sleep, and we wake up in the next day. Our plants are grown, so we can harvest this with standing on them. Oh, that takes them 2 days. Okay. Oh, okay. These guys must take more time. Okay. So I'm just going to show you the inventory quickly. I'm just going to sell all my produce. So what, we've got free wheat, let's sell it all. This gives us 15 gold. Very nice. Then we can buy some more wheat. So I just bought 15 wheat seeds. So, I could then go along and start placing more wheat. I could start getting, a bigger farm on the go. And unfortunately, gold doesn't really do much. The original intention was to have a full-blown vendor system where you could upgrade your weapons, your axes, your pickaxes, which will be used to mine these resources. There was also supposed to be a full-blown boss fight in the game as well, which would have been in the castle over here. This is where you would be facing off against Timothy, hence the name Timothy Must Die. There was also supposed to be a forest, a mines, and a town scene, which unfortunately did not come together in the time. Which is unfortunate. I would have loved to see those come together. So yeah, I think that covers where's the fun, because it's quite vibey game. There is some solid vibes in the daytime with these ambient sounds, like actually like mining and hearing some sound effects. Honestly, the sound effects really have brought the color completely together. The sound effects and its lights, the really nice polished features. A better UI would be nice, but there is a lot of really nice polished features in the game so far. So I think the fact that this game was developed within really the last 2-3 weeks shows that this framework has potential. It has potential to make good games. It has potential still to be improved. It has potential to, actually create games that you could put on sale on Steam, etc. There is still more room that we could do to improve things. So what did the game require? Well, it required the tile map system, it required the physics, it required collisions, the A-star, the AI controllers, the health, a fighter system, movement system, scene managers, the renderer. It required seeds, farmland managers, resource nodes, sprites, component. It featured practically 90% of these files here. There is so much going on in the back end of this, and I think we did create a really solid MVP of a good game that could be developed in this. The genre of the game, I mean, it's obviously what I'd say it's like a top-down RPG, casual top-down RPG with some like farming and resource gathering. So ideally, the resource nodes would disappear after you mine them, and then they'd be in the forest, and they'd sort of randomly generate each day to give you like tasks to do each day. We wanted fishing mini games and food and consumables, which would be really nice to put in. Having NPCs you interact with and cutscenes and stuff like that would be really nice as well. Yeah, I mean, I've been describing future work throughout like this entire demo actually, so I think that does show how passionate I am about how this project turned out and the game produced and the framework produced. It is got some true potential to create a good game and a good framework that could potentially be used as a open source framework for lots of indie developers to go through and actually create their games in it. And that would be a fun project to do, I think. I'm going to show you some rather hacky code now, some code that really could be improved. So the A-star algorithm. A-star algorithm is usually not hard. It's usually a pretty small amount of code. This A-star algorithm turned out to be hell. Something about it just would never correctly work. There was horrible optimization issues because, well, we've currently got it so there is a like 16,000 size tile map or something. That's a lot of tiles. It needs optimization. So we didn't really do much of that optimization. So that's a lot of where the performance gaps are doing. To do that optimization, we'd probably have to do a chunk system. So we could say, okay, a chunk is 16 by 16 tiles. Only build a new VAO for this chunk when you update it. Only update the A-stars area for this when you update it. The A-star algorithm could then do a path from chunk to chunk and then do the final path inside. There are lots of potential ways to optimize this further and actually make it more sort of industry standard. There are some areas in the project where it's clear that they have not been documented. Well, the code is not as self-explanatory as I'd wish it to be. For example, this is mainly just a lot of maths with no explanation of the maths. If you look at the renderer, it's just solid work with but then the header's documented, so people don't have to know how it works. They just see these methods, and that's all they do. So yeah, I think there's still a lot of room. There's a lot of room for improvement. There's a lot of room where things were definitely done wrong. Yeah, I think that's my conclusion of the framework. There's so much more that could be done, but it's also done so much already. Anyway, thank you for watching. So Adam Harris, and goodbye.